Okay, good evening everybody. Welcome to this joint meeting between the British Tunnelling Society and the MinSouth Society, and I welcome on behalf of that society Mark Davis, who is the current president. So once a year we have a combined meeting to acknowledge the connections between mining and tunnelling. So this is what it's always held in February. So tonight's talk is going to be on the Woodsmith Mine Project. Do you want to say anything? Say hello?
No, well,
just say hello to these nice people.
Hello, nice people.
Okay.
I'm Mark Davis. I'm a geologist, and obviously I've been on the committee of MinSouth for some time. MinSouth is associated with the IMO3 group. Thank you.
Okay. All right, moving on to our speakers then. So our first speaker is Jeff Hawman. He's the Woodsmith Mine Manager, Anglo American. Jeff holds an MSc in Mining Engineering from Campbell School of Mines and a BSc in Mathematics from the University of Manchester. A Fellow of IOM3 with over 20 years experience in the UK mining industry. Jeff holds single-point client responsibility for the execution of works on the MTS tunnel and related infrastructure, and is appointed under the 2014 Mines Regulation to be responsible for the safety and management of the Woodsmith Project tunnelling sites. The second speaker will be Tom Wootton, Construction Manager for Tunnels and STRABAG, qualified again from the Campbell School of Mines with a mining engineering degree. Progressed into the tunnel industry working on projects such as Crossrail, Thames Tideway before the Woodsmith Project, responsible for tunnelling activities on the project. A third speaker will be Callum, who's the Construction Manager for the Surface Works STRABAG, a chartered civil engineer with over 10 years experience in delivering major civils projects, responsible for the construction of the deep access shafts and general surface works on the project. And the final speaker will be Ashley Poulter, who is the Deputy Project Director for STRABAG. Ashley is a chartered engineer and member of the IOM3 with 25 years experience in tunnelling and mining projects, including CTRL C220, HS1, Coombe Down Stone Mines, Crossrail C305, Hinkley Point C, and Woodsmith Mine. So, can I ask the first speaker to come up, please?
Good evening, everybody. I'll just give a quick overview of what's in store for you for this presentation. I'm starting off, I'll give an overview of the project, Poly4, our product, our crop nutrients product, a little bit about regulation, and then sustainability. Then Tom Wootton will talk about the tunnel in more detail, and then Callum will talk about our intermediate shafts, and then Ashley will talk about the challenges and some of the successes that we've had on the project. So firstly, I'll start with the product, which is the reason why we're building the Woodsmith mine. It's Poly4 is the trademark name for our polyhalite products from Anglo American's crop nutrients business. It's a multi-nutrient, low chloride fertiliser, and it's certified for organic farming. It contains 4 of the 6 essential macronutrients required for plant growth, namely potassium, calcium, magnesium, and sulphur. This is a plan view of the Woodsmith Project. It's based in the north of England, from Teesside down to the North Yorkshire Moors National Park, which isn't necessarily the place that you would typically expect to be developing a Tier 1 mining project. But the mine is an opportunity for Anglo American and also for the region and the UK in general. In addition to the capital investment we're making, the jobs that we are creating, and the social programmes that we're investing in, We're also building an extraordinary project which will help improve skills in the area and prepare us for future opportunities. You can see from the slide in the red, that's the lease area for the project, and it's significant. Currently, we're only focused on this small area for our ore reserve and mineral resource, which is the purple colour. This small area is made of 290 million tonnes of reserves and inferred resources. In the life of asset plan, giving us approximately 40 years of life, and the exclusive mineral resource is approximately 2 billion tonnes, which gives us potential for decades to come, beyond the first 40 years. Other key features of the mine are the 1-to-1 ore to waste ratio, and we are targeting at full production 13 million tonnes per annum. In relation to the resource, it's not the only one in the world, but it is the largest known deposit of polyhalite in the world. And we have a unique resource with the size and scale needed to be a multi-generational mine. A sectional view of the project. So red is current progress. Firstly, we're starting at the left-hand side. That's the Woodsmith mine site. There's two 1.6 kilometre deep shafts, the service shaft and the production shaft. These will be sunk to the final elevation by our shaft sinking contractor Redpath. When done, these are expected to be the deepest mine shafts in Europe. From a status standpoint and where we are today, the service shaft is at 804 metres and the production shaft is at 712 metres. The production shaft has benefited from quite a lot of the lessons learned from the service shaft, which was started sooner. And we're very pleased with the progress that Redpath have made in the shafts since they started in 2022. Slightly to the right of that on the drawing is the mineral transport system shaft and the MTS level underground facilities. That'll handle the polyhalite ore, which will come up the production shaft and will be transferred onto the tunnel conveyor. Thirdly, going from there to the port is the tunnel. So this is a 37-kilometre tunnel underground transport route, and it'll be used to carry material from the mine to the handling facility at the port. And today we are at 29.3 kilometres in. Along the route of the tunnel, there's two intermediate access shafts at Lockwood, Beck and at Ladycross Plantation. And to complete the picture on the right, we have a materials handling facility that's planned to be built at Teesside at Wootton, and a port facility into the River Tees. These sites where the polyhalite will be granulated and loaded out for shipping. So looking at these photos, you can see how different the Woodsmith project is to a traditional mine and the infrastructure approaches used in the past. This is the standard we are setting for the future of our industry and is something that we're very proud of. So Woodsmith is without a doubt the industry benchmark project in sustainability. The future visual is the top left picture there of the finished mine site, what it's expected to look like. When in operation, you wouldn't really know it was there. It's just going to look like farm buildings. In addition, we have very little impact to the area around the mine site due to the use of the tunnel to manage the material from the mine to the port, limiting the number of people and materials coming to site. To compare, you can see on the other pictures waste dumps, transport infrastructure that others have had to build in the past. And you can see the visual impacts with large head frames above ground, long railways and significant dumps. They'll have their legacy and we will be the opposite. And this isn't just for operation either, this is also during construction. We abide by strict limits on lighting, noise, traffic, emissions and water to minimise impact to our neighbours in the National Park and elsewhere, and to the environment, and actually expect to achieve a net positive impact on local biodiversity. We're setting a new benchmark on how mining will be done in the future today. This is a picture from last year of the Woodsmith mine site. You can see in the left there, that's the MTS shaft with the headgear. That'll all go when we go into operations. And to the right of that is the production shaft and the service shaft with the headgear underground in the four shafts. And so this is actually a photo of the production shaft prior to the roof and the head frame being installed. So it's an excellent photo to show how the shafts were constructed to minimise surface and visual impact. So what you see is the foreshaft, which is a concrete encased structure around 43 metres deep. This houses the mine shaft, which will be used to move people and materials up and down to the mine. This structure, again, around 43 metres, would normally be on surface and be seen for miles around. But since this is being executed in a national park, and we are integrating with the needs of the community, we have sunk all of the steel below ground. And this translates to a mine that has very little visual impact during construction and even less during operation. We're using shaft boring road headers, SBRs, to excavate the two deep shafts. These SBRs are an updated version of those that were used on BHP's Janssen project and also in Belarus. So these machines are inherently safer than traditional sinking. They also reduce the need for explosives, which is a huge benefit, and they're just safer, quicker and more predictable. Before Tom goes into more details of the tunnel, I'll just show you where we are compared to the port and the mine. So the tunnel portal at the top left of this picture is at Teesside. All references are in kilometres from Teesside. So Teesside is effectively our working base for the tunnel, and where we have the concrete segment factory, where the segments for the tunnel lining are fabricated and railed down to the TBM. Along the route you can see the two intermediate shafts, providing access for people and materials, as well as ventilation and power. Both intermediate shafts are fully excavated and lined, and Callum will talk about that in a bit. The first at Lockwood Beck is 100% complete, and the second shaft at Lady Cross is in the final throes of its fit-out and connection to the tunnel. So the tunnel, it's the backbone of the project and the future of the operation. It will be the conduit to provide the mine all the essential services for the operation, including power. It is our main transport corridor for the product via the product conveyor, and the tunnel eliminates many of the environmental and social impacts that mines typically have, especially with the communities. Ultimately, this is the most efficient and reliable transport system for our mine, and is another key reason why we will be low cost, low carbon mine. So since the start of the project, the progress from the TBM has been excellent. There are many positives to talk about the tunnel construction, the main ones being, firstly, our contractors STRABAG. They're one of the world leaders in tunnelling technology and successfully executed numerous large and technically complex tunnelling projects in many jurisdictions, and they are a world-class tunnelling contractor. One of the key features of the tunnel is that the ground conditions over the full length of the tunnel are very consistent within the Redcar mudstone. Conditions are very predictable, and cutting has been easy for the machine. By every measure, the tunnelling on the project has been an amazing success. So this slide is about our planned material handling facility at Wootton to prepare the polyphore granule product. So compared to many process plants in mining, this is very straightforward, as you can see from the simplified flow sheet. So we crush and grind the product, mix the product with a binder, granulate to produce 2 to 4 millimetre granules, and then it's dried and coated with a wax coating to protect it during transport and spreading. There's been considerable time spent over the last few years optimising the flow sheet via our on-site research and development facility, also at Wootton. And we are now satisfied we have the right flow sheet with known technology that can deliver the granules needed by the farmer in the field. So nowhere in this process is there any kind of chemical processing like muriate of potash. It uses very little water. Everything produced at this plant will be sold around the world and in the UK. So the photo on the left, that's the segment factory at Wootton for the tunnel. Once segment construction is completed, that area will be cleared and the MHF facility will be constructed over that area. And that picture on the right is what the future MHF will look like in full operation. And the final piece of infrastructure for the project is our deep water port that we have at Bransands on the River Tees, just a few kilometres from the tunnel portal. So we have our own fully dedicated, it's fully permitted deep water port. And once this facility is constructed, it will be able to handle all 13 million tonnes per year. Also nearby is the existing Redcar bulk terminal port, and both are near the exit of the River Tees to the North Sea. So dedicated port facilities, again, the theme of key structural benefits for the mine. Just talk a little bit about the regulation of the project. So quite unusually for this sort of tunnel, the Woodsmith Project is regulated by His Majesty's Inspectorate of Mines, and the principal legislation is the Mines Regulations 2014. So this is more understandable for the actual Woodsmith mine site, but for the tunnel scope it is unusual. It would normally be CDM, Construction Design and Management Regulations. The reason for this lies in the legislation and the purpose of the excavation, which is extraction of minerals. So this falls under Regulation 3 as being classed as a mine. And this different approach introduced change to the tunnelling construction and the risk management methodology. We believe it's the first time that a tunnel of this type has been constructed in the UK under the mines regulations. Some of the differences that we've found in the last 6 years is the different relationship between client and contractor. So Anglo American, as the client, is also the mine operator, and they have specific duties under the regulations, particularly around safety. So we've had a very close relationship with STRABAG over the years, over things like especially safety, training, competence. A lot more presence from the mine operator, from the client on site than what would be normal. Appointed persons. For example, myself, I'm appointed under the regs. I have superintendents and engineers also appointed. And likewise, the mine manager at the mine site also has an appointed team. One of the differences is the regulator, the HMI, are extremely proactive. We have regular major hazard interventions. Just to put it into perspective, the tunnelling sites have 4 interventions a year on major hazards, whether it be fire, inrush, escape and rescue, and then we also have 4 at the mine site as well. But we believe that the increased scrutiny has been a positive driver for a safer operation. Escape and rescue, again, under the regulations, there's very stringent requirements under the mines regulations. We have on-site mines rescue teams. We have an enormous amount of equipment across the sites for escape and rescue. Again, a significant extra cost, but we believe a large benefit. The management of major hazards, that's been under the regulations, the mines regs, there's a very robust and systematic structure for the control of major hazards. So we do bow-tie analyses, safety performance indicators are used a lot, hazards, and again, this has driven a much safer project, we believe, the way that we've handled the major hazard control. And finally, maintenance and inspection. There's extensive written schemes for both of these, as is required under the mines regs. There's an awful lot of extra resources have been put in place for the maintenance on the project, and likewise for the inspection, workplace inspections, safety critical inspections. There's a huge inspection regime in place. Finally, slide on sustainability. There can't be a mine without sustainability these days, and this is at the core of everything that we do at Woodsmith. You can see from the slide that Woodsmith will play a major role in sustainability in the local area and globally. From an environmental perspective, the mine is designed to blend in with the landscape, ultimately to look just like a few barns on a farm. We manage noise, light, traffic, biodiversity with very strict limits and dozens of permits in place. The fact that we don't have significant processing or transportation on surface of ore means carbon, water and waste are minimised. For the community, we've generated $1.5 billion into the local economy since construction began. And Anglo American has committed to contribute $1 million a year to the Woodsmith Foundation, which has supported 550 projects so far. It's an independent charity with 5 objectives focused on education, health, hardship, environment and community facilities. All of these aligning to Anglo American's values and goals. And finally, as the mine ramps up and succeeds in meeting its goals, the community benefits as we contribute 0.5% of our revenue during operation, roughly $10 million per annum. Our success and the community's success are intertwined during construction and operation, and this is really how the business should operate. And from a people perspective, the local area has low job density compared to many other areas, with many low-paid, low-skilled, part-time jobs. And to date, we've created over 1,000 new jobs in the mine, with 70% being from the local area, including 42 apprentices in engineering and cybersecurity. And we are committed to growing a local workforce that will have the skills that we need in the future. Okay, thanks. I'll move on to Tom for the tunnel. Cheers.
Thanks, Jeff, and thank you for the kind words. So I just want to run through a bit of an overview of the tunnelling side, what's involved in the STRABAG scope. Jeff's given a great overview of the project as a whole. For us at STRABAG, our scope, so Jeff's touched on the Wootton surface setup, the on-site production of segments. So we have an on-site steel hall that fabricates the steel reinforcement, and then a segment factory which fabricates the segments which have contributed to the tunnel. We have a 300-metre launch ramp and 100 metres worth of SCL tunnel that was constructed to facilitate the launch of the TBM. We then have the 37-kilometre MTS tunnel, 2 intermediate shafts, so Lockwood Beck at 12.7 kilometres from Wootton, and Lady Cross shaft as well at 28.5 kilometres from Wootton. And we also have the SCL connection adits between the two, so between the MTS tunnel and the 2 shafts. Looking forward, we at STRABAG, we think we're in a good position for future tunnel fit out. Like Jeff said, it is the whole purpose of the project is to be able to extract the polyhalite, the poly4 from underground and impact as little as possible on the environment. The permanent conveyor and potentially tunnel enlargements as well in the future for us. Now, a 37-kilometre tunnel, the programme and scope have been amended over time. We certainly didn't set out with the intention of launching 1 TBM from Wootton and making all the way to Woodsmith. I'll take us back a little bit then, at the very start of when STRABAG started on the project. So the original contract and programme, the 37 kilometres was split into 3 TBM drives, each approximately 12.5 kilometres in length. Drive 1 had been awarded to STRABAG, and that was from Wootton to the Lockwood Beck shaft. The Lockwood Beck shaft itself was being delivered by others. It was being sunk conventionally with a 9-metre diameter to facilitate the launch of a second TBM for Drive 2. And the MTS shaft was going to facilitate a third TBM coming from the Woodsmith side and meeting up with that second drive, approximately the 26.9 kilometre mark. At that point, the Lady Cross shaft, although there was planning, wasn't deemed necessary as it wasn't a launch site or reception chamber, so it wasn't part of the planned works. As works progressed, as the TBM was launched, progress proved very successful. There were also some issues at Lockwood Beck. There was programming problems, and the TBM within a short period of time was bearing down on the Lockwood Beck shaft, and there wasn't the availability to launch a second TBM from Lockwood. This meant that there was an amendment to the contract. It reduced the total drives, or the TBMs required for the drive, from 3 to 2. The intention being that the TBM launch from Wootton would continue on, and that would go past Lockwood Beck and go to the 26.9 kilometre mark, and then the second TBM would be launched from Woodsmith. At this point as well, they were intending to meet at the 26.9 mark, so the Lady Cross shaft, although it wasn't vital, it was then included in STRABAG scope, just in case in the future we came to a 1 TBM solution if the production rates were sustained for the second half as they had up to Lockwood Beck. Fast forward a little bit further, and we did maintain a lot of those production outputs. The TBM has done a fantastic job, and the teams that have been operating it, and all the backup teams that go with it. There were some programming clashes as well as works progressed on the Woodsmith side with the MTS shaft. So we went away, STRABAG, and we were asked to look at the feasibility of the 1 TBM solution with everything that we'd put in place to get to approximately 18, 19 kilometres by that point. And we came back and essentially said, yes, we think it will be possible. At that point, we were glad that the Lady Cross shaft had been added to our scope, and Callum will touch on that. But that's initially how we've got to the point where 1 TBM is doing the full 37-kilometre tunnel. As a nice aside to that, it does mean that we currently believe we've got the world's longest single-heading tunnel, the previous being 25.8, and we've surpassed that. Going on to the construction milestones, I'll give a few key dates. So going back to 2018, it's been a long project. So April 2018, we started off with selection of the single shield hard rock TBM. Within 10 months it was on site, and 12 months it was fully assembled. So April 2019 it was ready to move. In the June of the 2019, the TBM then started its first advances. By October the following year, so 2020, 14 months later, we were at the 10-kilometre mark, and roughly 14 months after that, we were at the 18.6 kilometre mark. At that point, 18.6 kilometres is beyond the Lockwood Beck shaft. We were feeding everything from Wootton. We came to a stop at that point with the TBM. Came back, the Lockwood Beck shaft had been sunk, and we were then in a position to connect up to that from the MTS tunnel using a shotcrete-lined connection at it. Also, as part of that stoppage, we did a refurbishment of the cutterhead and built a crossing outside of the Lockwood Beck at it. Approximately 6 months later, so August 2022, we were in a position to restart the TBM. So a couple of images there showing the Lockwood Beck conveyor booster that had been installed on the crossing just outside the adit. So the adit was complete, the cutterhead refurbishment, and we were in a position to restart. Following year, May 23, the TBM was at approximately 23 kilometres, and we paused to install another crossing location. Up to this point, we'd been running with 2 crossings. It was about time we added a third. The majority of the tunnel is single track that I'll come on to in a second. October of that year, 2023, we passed the 25.8 kilometre mark, and then January 24 last year, we passed the 26.9 kilometre mark, which is originally the end of Drive 2 and into Drive 3. Middle of last year then, 2024, the TBM just got past the Lady Cross shaft location, 29.2 kilometres. At that point, the shaft was ready and waiting for us, so we parked up again and did a very similar exercise as what we'd done at the Lockwood Beck connection. We had a technical stop, constructed a crossing, conveyor booster, added connection to the shaft, and also conducted refurbishment on the TBM. December last year, so just before Christmas again, we were in a position to restart the TBM. That's a quick overview of key dates. If you put all that hard work and many millions of man hours onto a graph, that's what it looks like. There's a lot of work gone into it. But we're very proud of the performance that we've had. Some of the numbers there, hard average, excluding the major technical stops, is over 20 metres a day. If you do include them, it's 16 metres a day. Best day to date is 52.7 metres, and the best month over a kilometre. A lot of the pauses that you can see there in production of what we just discussed with the technical stops and planned downtime. So the current position, 29.3 kilometres, and we are approximately 190 days ahead of programme, and that's something, again, we're very proud of. So a little bit about the machine, the tunnel boring machine that's achieved this. So it's a 6 metre bore diameter, 252 metres long, comprising 20 gantries. The segmental lining is 5.6 metres external with a 4.9 metre internal. That gives us an annulus of approximately 200 millimetres, so we inject 6 metre cubed of primary grout into that annulus. The segments are 1.5 metres wide and 350 mm thick, roughly about 3.5 tonnes, and all fabricated at the Wootton site. The 6 segments to a ring and the universal tapered rings. We have variations in the type of rings that we use depending on the overburden or exposure class, but in terms of dimensions, they're all the same. So there's variations in the concrete grade and amount of reinforcement. On the TBM, we have capacity to store 3 rings. So there's three rings for the lifters. We can also then have an additional ring on the feeder. So the machine has been able to put output high advance rates. We can achieve an advance and build cycle in approximately 30 minutes. So an advance taking 15 to 20 minutes and a ring build 10 to 15 minutes. The machine itself, it's got a large main bearing, so it's got good access to the cutterhead. It's a very strong machine, max thrust force of 6.2 meganewtons, which is coming helpful with some of the stoppages that we've had with the overburden that's above us. To be able to complete those stoppages, we've had to take the teams off the TBM, go back and complete the works, and it's meant parking up the machine in, we assess the ground and park it in as competent as grounds as we can manage. On one occasion, we have had to get close to that maximum limit of thrust, but she's always broken free again. Some of the infrastructure, as I've said, it's a single track for the majority of the tunnel. I'll come on to the crossings in a second, but they only make up a very small percentage. The majority, approximately 27.5 kilometres of the tunnel is single track. It's in 9 metre sections and brought from surface down to the TBM, so that's over 3,000 sections of track that have been installed. There's no designated walkway in the tunnel. We have lighting stations, so designated hop-ups for team members to get off within the tunnel. Then it's used in the track, so we've had to separate people and plant through maintenance shifts and production shifts. HV power, originally supplied from Wootton, is now supplied from Lockwood Beck. Ventilation, again, a key aspect, has been forced. It's initially forced from Wootton, now moved to Lockwood Beck, and once the Lady Cross adit fit out is complete, we'll be moving the fans underground into the Lady Cross adit, and they'll be forced into the TBM, and then exhausting all the way back to Wootton surface. Cooling water is supplied from Wootton. again pumped 29 kilometres, and then dewatering in the tunnel, again pumped back out again, a further 29 kilometres with 17 stage pumps. Grout, so supplying the grout to the TBM. This is one of the many achievements that we're very proud of and that we've achieved on the project. But we've been able to pump grout from surface, maintaining its quality up to 18.5 kilometres within a pipeline within the tunnel to the TBM. That's removed the need for grout cars, and it's been one of the many contributing factors to the TBM success. So initially, up to the 18.6 kilometre mark from Wootton. Once we then had the connection through at Lockwood Beck, we could move the grout plant forward. That carried us an extra 16.3 kilometres until we got past Ladycross, and now we've moved the grout plant to Ladycross, so it's 1 kilometre. That's to try and give you an idea of the scale of some of the infrastructure that's had to go into the tunnel. At points there, we had 60 cube of grout within the line. Pumping over those distances, any small delays, and we had a few, can quickly give you problems if the grout's starting to go off. Logistics within the tunnel. Currently we have the 5 crossings. So working from Wootton on the left, District 1 in the pink, that's approximately 6 kilometres. So from Wootton to the first crossing, we've got 6 kilometres. That's a fixed crossing in that location, steel construction, a single loop for trains to pass. After that, District 2, another 6 kilometres until we get to Lockwood Beck, with a double loop, one side of which is where we enter the Lockwood Beck adit, so that's primarily closed off. Districts 3 and 4 then, with the 21 kilometre fixed crossing in between. Those 2 districts are 8 kilometres each, and then we get to Ladycross, the latest that's just been installed. There we've installed 3 loops so that we can allow trains to park up and pass. In total, we've had 22 locomotives. They're a mixture of hybrid and full electric, so diesel electric hybrids and full electrics. Running up to 5 production trains at one time, which is a tandem set, so a hybrid and an electric. Currently, the travel time from Wootton for a production train or a maintenance train to get down to the TBM is 1 hour 50. A lot of planning has to go into making sure that the operation runs smoothly. It's not a quick fix, just to nip back out to the stores if you forget a pair of pliers or such. A very brief overview of the geology. So the first 800 metres of the tunnel is through glacial till. Initially that was going to be all SCL, but after the first 100 metres or so, the ground conditions improved and the decision was taken to finish the SCL tunnel at 100 metres and launch the TBM, which proved to be a good decision. Beyond that, primarily we've been mining through the Redcar mudstone. It's a weak, relatively low permeability rock, but there are areas with ironstone nodules and variation within the subclasses of Redcar mudstone. The tunnel itself is relatively straight. We don't have to worry about too many curves. Maximum or the minimum curve radius is 6,000 metres, but the maximum overburden is 400 metres, so it's deeper than a lot of other tunnels currently in the UK. Along the alignment, there's 15 major fault zones. We're currently approaching the 14th of the 15. We've also passed under various mine workings, potential for water if they were connected, approximately 100 metres, within 100 metres of some of the old ironstone workings. And we also have experienced a little bit of methane along the project, although it's not necessarily been linked to the fault zones. So the mudstone and the fact that we've a hard rock TBM with the hard rock cutterhead, it's generally given us low abrasivity. There's been a low turnover of wear on the front. But after the distances involved, we have had to do some repairs to the tunnel boring machine. In general, throughout the life of the TBM, we've done our utmost to ensure that maintenance is carried out on the back of the machine, but there are areas, i.e. the cutterhead, that you can't necessarily access normally. We've been fortunate to have the Heron Connect expertise on the project. We've also made changes ourselves. There's been several adjustments to shift patterns. Whilst it's nice to have 24/7 production, 4 or 5 times across the project we've introduced more and more maintenance periods to ensure that the infrastructure behind the TBM that I've touched on there is in a good condition to be able to maintain a steady output. In terms of wear on the cutterhead, we do regular inspections. Cutter discs we can replace from within the cutterhead. Generally, they're a low turnover. However, over time, there was indication that, especially around the gauge of the cutterhead, there was a lot of wear starting to occur. Primarily on the hard ox wear plates. And the decision was taken that we would need to be able to access the front of the machine to conduct repairs. This decision was married up with the stoppage for the Lockwood, Beck and Lady Cross adit connections. So the teams, being a single track, we were unable to sustain TBM production whilst doing those works out by. So the teams split up into 2. Some going off to work in the adit, the others to construct a timber heading to give us access to be able to then repair the cutterhead. Being 360 metres underground on average, it's unviable to access from surface, so an underground access had to be formed, and after various iterations of design, the final decision was the timber heading. This piece of work was undertaken twice, like I say, Lockwood, Beck and Lady Cross. On the last built ring, when we came to a stop, the key segment was removed, and that provided access to the mudstone behind. The excavation profile was 1.6 by 2.1, with the timber frames given an internal profile of 1.4 by 1.8. Relatively tight confines as timber headings are, albeit not normally at this depth. We managed to mechanise as much as we could. A lot of the excavation using a Brock 70, very capable, especially for its size, and mini conveyors underground to reduce manual handling. Once the access was formed, we have had incidences of methane, but given the excavation time, a lot of that had dissolved, and we were able to manage the hot works effectively. Once we were complete with the repairs then, we backfilled those timber headings, reinserted the key segment, and once the Lockwood, Beck or Lady Cross adits were complete, the TBM was able to continue. So as of December, we've finished the second repair, and hopefully it's good to go for the remaining 7.5 kilometres. Okay, I'm going to pass over to Callum, who's going to take us through the shaft construction.
Great, thank you, Tom. Good evening, everyone. So as Tom said, I'm going to take us through the shaft construction. We'll have a look at the shaft locations, the requirements of the shafts, the method that was chosen. I'll give a bit of a whistle-stop tour on how that method works, and then some of the benefits and opportunities from the blind boring. So Tom mentioned previously the first shaft that was required from STRABAG was at Lockwood, Beck. The initial plan was for that to be a launch site for a TBM. However, things changed throughout the project lifespan, and it meant that there was a significant change needed. A launch shaft was no longer required. The contract had been amended to permit the continuous operation of TBM1 past Lockwood, Beck and towards Ladycross. However, the services supplying the TBM were starting to reach their capacity, namely ventilation, which could take us through to 18 kilometres, around 5 kilometres past Lockwood, Beck. Grout was starting to see some issue. Power was a single source, so there was opportunity to back up our supply. But also from a safety standpoint, we were single entry. So from a rescue perspective, there were some threats to us. And also from a logistics viewpoint, it would take a long time to get us from Wootton to the current TBM position. The key challenges that we faced, it was a change to the overall scope, and it was a change that meant that the programme fell onto the full project critical path. So that was kind of one of the key drivers for the decisions that we were therefore had to make. Geotechnically, there were faults within the Lockwood Beck site, and there was also groundwater which caused challenges to the previous thing. So a contractor working on the site previously had sunk a shaft to around 50 metres, and there was significant challenge with inflow of water up to about 200 cube an hour, and the solution to grout that was a sore challenge. Environmentally, we were on the border of the national park, so that brings its own kind of environmental sensitivities. So the shaft that was needed, depth-wise at Lockwood Beck was 378 metres. We had a number of different parameters that we had to therefore fit into the shaft, and that's what made came into our decision making. The Alimat lift car would lift 16 people up and down the shaft. Ventilation would be fed to the TBM, but also as a fresh air base at shaft bottom. Mechanical services of grout and water, as I mentioned. Electrical cabling, comms, lighting, and then a head house with the provision for rescue. Assessment was done to consider how we could reduce the diameter of the shaft and then introduce new potential construction methods. And we ultimately came to an internal diameter of 3.2 metres would suffice. We assessed then the various options of excavating and constructing the shaft. And as I said, one of the key parameters for us here was programme. After various assessments, blind boring was selected as the primary option for us. For those who've not seen it before, what is blind boring? So ultimately it's a deep shaft construction methodology. It's an alternative to the conventional drill and blast, where works are undertaken from surface until the shaft is complete. It's much more commonplace in Australia and the United States, where the method is used for ventilation shafts to the mines. It's also been seen in the UK and South Wales in the 80s for a similar ventilation shaft. We employed a contractor, and we worked very closely with a contractor from the States in Shaft Drillers International. SDI have rigs capable of shafts up to 5 metres in diameter and up to 550 metres in depth, so it fit our parameters. We also use, where possible, the local supply chain. A key example of that is the shaft lining. And ultimately, as an assessment, why blind bore? So it is faster, safer, and more cost-effective than conventional methods. And for us, it provided us with the TBM supplies that we much needed to continue the TBM drive without impacting our critical path and working through some challenging ground conditions. So the methodology of blind bore, there's 7 phases here that have been broken down. I'll take us through each one of those. I haven't got enough time really to go into much detail, but I'll take us through the kind of key aspects of each item. So firstly, pre-grouting. Ultimately, pre-grouting is integral to the success of the methodology. Grout holes are drilled around the circumference to varied depths, and it's a top-down observational approach to heal the ground. The objectives are twofold. One is to stabilise the ground to avoid any collapse, and secondly, to ensure that the body or the ground can withstand a body of water, which is essential for the following stages. In terms of numbers, at Lockwood Beck, we pumped 810 tonnes of grout over 47 holes. I just also wanted to mention at this point, at Lady Cross, and I'll come on to mention Lady Cross briefly towards the end of the presentation, but at Lady Cross we also introduced an environmental curtain. That was a secondary grouting ring on the extrados of the cementitious grouting curtain. We used a colloidal silica to externally cut off any cementitious and risk of any cementitious material polluting drinking aquifers. There was an increased cost of doing this. It was an unknown and a challenge, but it reduced our risk and simplified the cementitious program. So just some very quick numbers, there was 920 tonne of colloidal silica pumped over 44 holes, and you can see that that did reduce the actual cementitious grout take in the second pass. Once complete, a pilot hole is drilled. This is a guidance hole which directs the blind bore. So using directional drilling methodology, a hole of about 440 mil diameter is drilled full depth with technology to keep it vertical. For us at Lockwood Beck, survey was showed us to drill the hole within 87 millimetres at 390 metres in depth. At this point, it also gives an indication of the successes of our pre-grouting programme. Following that, the fourth shaft is constructed. To do so, there's a secant pile wall. In our case, it was 4.3 metre ID, down to 25 metres. So it's end bearing in the competent rock below, and then on surface is a drill pad. And ultimately, what we're doing there is taking the loads from the drilling rig and drilling operation, passing those through to competent ground. And it's ultimately a watertight structure which prevents the potential washout of superficials in the upper ground. A picture, as you can see just on the top there, that's actually our Lockwood Beck site. It gives you a kind of a feel of the size of the equipment. In the background there's a large 10,000 cubic metre sedimentation lagoon, and on the left you can see some of the casings that were required. The other equipment on surface were from a hangover from the previous drilling methodologies. So once the shaft is ready to be drilled, there's a hemispherical cutting head which is lowered into the shaft, supported by the A-frame on surface. Kentilage is applied on top of that, and that's lowered into the shaft. A turntable is placed on surface, and that provides the rotation, and as the cutter teeth engage, it cuts the rock. Reverse circulation process is then brought in with the use of air injection to create a differential pressure in the ground, and therefore an uplift of the water within the shaft. As I mentioned before, it's essential that a successful pre-grouting regime maintains that head of water to enable that to therefore happen. Drill string is added as the shaft proceeds, so just continuing to excavate down to full depth. And just to give a flavour of time frame, our hard average was about 4 metres per shift, taking 7 weeks roughly to excavate the shaft. Upon completion at this point, there's no lining within the shaft. So the equipment is taken from within, and then the liner is installed again from surface. So at this point, there's still no personnel within the shaft. The liner, which were sourced locally, at Lockwood Beck, there was 43 of them, ranging between 15 and 30 millimetres in thickness, 9 metres in length, and increased stiffener channels between 3 and 10 stiffeners, depending on their location within the shaft. The casings are around 25 tonne per length, and as I say, they're lowered into position, placed on the previous, welded, tested, and then lowered into the shaft. A buoyancy program is used to manage the loads that are seen. The full drill string weighs around 1,000 tonne, but we have to overcome the buoyant forces which are seen from the water within the shaft. So ultimately water's placed within, and that's balanced to then lower the casings down to the shaft bottom. Again, for a flavour, the programme here is about 5 weeks. Once the casings are lowered to the shaft bottom, the annulus between the cut ground and the casings is filled with grout in stages from bottom to top. And then the water from the introdos is pumped out, and the shaft is complete, ready for handover to the fit-out teams. As an overview of the benefits of blind bore, firstly is safety. So it's surface works only until a permanent watertight structural line has been installed. And there's small skilled crews working around the clock. Obviously, if you compare it to a conventional method, there's no requirement for explosives. And for us, as I mentioned a few times, what was key here was program. The methodology has many program advantages. For us here, we had a turnaround of 11 months from starting the process, from the grouting before the piling, to completion for fit-out in 11 months. Our estimations were that there was still a year's work to complete the setup of the winders. So we'd finished the shaft before we'd even potentially start excavating. In terms of the comparison, during the excavation and lining phases, we averaged 4 metres per day, around a 75% reduction in comparison to a conventional sink. And with minimal site set requirements and also the advantages of setting up and completing the shaft completely independently from the TBM drive, there was a number of schedule benefits for us. Environmentally, there's reduced noise and visual impact over the method with a reduced construction footprint and obviously no requirement for head frames or winder gears. Winder building, sorry. In terms of a comparison between a conventional sink, which I appreciate was 9 metres in diameter versus our significantly reduced diameter, there was an 84% reduction in spoil produced, and we assessed around a 60% reduction in carbon related to the construction methods. With a shorter programme, with less people and less infrastructure and setup, and also no secondary lining required, there's also a number of commercial benefits for the method. So was it a success? Ultimately at Lockwood Beck, which was the first of the shafts to be drilled, it was an innovation. It was a new innovation, a method that had not been seen and used in this way before, brought into the market. We collaborated very closely with our supply chain and between Anglo American and STRABAG, and we delivered on time, overcoming the challenges. We completed without safety or environmental incident. We then had the opportunity to repeat the process, as Tom has touched on, the overall project changed again with a single entry TBM and a 1 TBM solution all the way from Wootton to Woodsmith. And that can be facilitated with a second shaft, which was then instructed for us at Lady Cross. Again, a replica with similar benefits that I mentioned before, but we were now within the national park and we had a connection to a drinking water aquifer, so it brought a few new challenges. We took a lot of opportunity to assess the successes, but also with any project, the failures and opportunity for improvement, ran lessons learned sessions, and then had the opportunity to develop those solutions and implement them. I know we're running a little bit behind schedule, so I'll pass over them, but ultimately the Lady Cross shaft was successfully sunk in the end of 23, and as Tom mentioned, we recently connected through with the adit from the tunnel. Thank you. I'll hand over to Ashley, who will run us through the key challenges and successes for the programme.
Good evening, ladies and gentlemen. I think I'm a bit tight for time, aren't I, John? Okay, we'll see how this... There's only 48 slides to go.
No, you're all right, you're all right.
So I thought I'd cover some of the challenges and successes, and I think they go hand in hand on the project. A project of this scale and the distances covered brings numerous inherent challenges with it. And I think Tom and Callum and Jeff have covered a number of those, from pumping grout 18.5 kilometres to keeping a TBM operating successfully for 29.3. There's been numerous challenges throughout. I thought I'd start with the adits. So Callum has just talked about the shafts that have been sunk at Lockwood and Lady Cross. We had to connect those to the tunnel. I think the first challenge in something that we've encountered on the project is terminology. And mining and tunnelling sometimes have a lot of different terminology and a different language for the same things. So there's been quite a lot of debate. I've left it as added because that's what it said in the contract, but I think Jeff would say otherwise. So I think there's been a lot of transfer of knowledge between the mining side and the tunnelling side. It's been really interesting, and mapping across that knowledge and that learning has been really beneficial to the project. So the two adits, Lockwood and Ladycross, the shafts that Callum has just talked through were sunk offline, about 25 metres offline from the tunnels. We then had to mine out to those tunnels, and we used spray concrete lining with temporary bolts to get there. I've not gone into the detail here for time purposes, but I thought I'd show some pictures. At the top there, we've got the location of the opening, and this was at Lockwood Beck. We used needle beams to support the segments, and within the rings either side of the opening, we had steel plates cast in, and then we welded needle beams to those to support the lining temporarily whilst we mined out. And that was a 2-ring wide opening, and then mined in pretty standard SEL techniques, but with some additional bolts for temporary support out to the shaft. And at the bottom there you can see the shaft liner at Lockwood Beck, so those steel casings that were installed and grouted in place. Before we did that, we were quite concerned about the possibility of bringing water from the upper aquifers 360 metres above down to the tunnel alignment, and obviously a significant risk. So prior to doing that, the borehole log on the right-hand side is the full depth of the shaft, and we targeted areas below the lowest aquifer, and before we opened up the tunnel, we went inside the shaft and we drilled and injected rings of polyurethane into the behind the liner, so that by the time we got down to the base of the shaft, we tested for water. Initially there was flow, but that was quickly cut off, and we cut that off before we started mining out. So by the time we reached the shaft liner, things were nice and dry. You can see the vertical line coming down in front of the steel liner there is one of the tremie lines that was used to grout up the steel casing. So when the spray concrete lining works were finished, you've got the example on the left there. You can see the back of the tunnel lining, the precast lining, and because there is a crossing in this location, the proximity between the ventilation bagging, you can see in yellow there, and the orange of the locomotive, it's really, really tight. Space is at a premium in trying to fit these works in. So this is not quite finished. On the left-hand side, there was additional propping on the back of the lining, permanent propping that went in place and then was cast in. But the purpose of these adits was to provide primarily access and egress, but also, as was shown, ventilation, grout supply, power supply. And we needed to protect those locations. So the first 12 kilometres and the second at 28 kilometres, we need to make sure that they're safe for people to access and egress. So should there be a fire in the tunnel, for instance, we can protect both the shaft side and we can protect people in the tunnel. So we used mine doors. So we used a company, American Mine Door, who supplied fire-rated, 2-hour fire-rated mine doors that we could install either side inside the adit. So we could protect the shaft from the infrastructure in the adit, and then we could protect the adit itself from anything that may happen in the tunnel. So the top right, there's just a schematic of the adit itself. We had ventilation fan installed in the adit, drawing air down the shaft, and at the bottom, we had a transformer for the power supply at Lockwood Beck. And on the right, at the bottom there, you can see the finished product. So something that was initially quite a challenge, identifying as well mine doors with the right safety ratings was quite difficult. We ended up using an American company and a Chilean standard for mine doors. So a couple of other challenges, the locomotives, and Tom's mentioned we have tandem sets. They're a combination of electric and hybrid locos in each tandem set. As the project progressed, the tunnel got longer. Then one of the significant challenges was looking at the fire risk from lithium batteries. And this, when we first investigated this, and it was done between ourselves, Anglo American, and the Mines Inspectorate, there was very little guidance, no regulation, and very little knowledge, I think, in the market. There were some guidelines we found from the Global Mining Guidelines Group, and there were individual papers, but it took a lot of research to assess how we can manage those batteries safely and ensure that we're not putting people at risk. There were a lot of controls developed as a result of this. The control of the rolling stock movements, we needed to make sure we know where each loco is. The tunnel split up into districts, which is mining terminology from the mines regs. And we can only have one loco in any one district at a time. So we needed to prevent collisions. We had to understand the battery chemistries and make sure we had the lowest risk battery chemistries. In this case, it was lithium titanate. And then understanding the battery management systems and understanding how the locos are operating by going through the black box data. So lots of controls put in place to overcome the challenges from the regulator as to how we know what those risks are. Another key challenge that Tom touched on was flammable or explosive gases. So there was one incident in 2020, November 2020, where a pocket of methane was encountered and we had an inrush into the TBM. Everybody was evacuated, but that inrush was fairly significant. It was estimated about 800 cubic meters. So this was unexpected at the time. There was nothing preceding that to indicate an inrush of that volume. But as a result, there were lots of changes put in place. And those changes included changes to the electrical systems on the TBM, automatic cut-off systems, and changes to the ventilation to ensure that we can purge the machine more effectively, that we can dilute, disperse, but also to the emergency arrangements, making sure we can get people out quickly. And that included a rescue train, which is essentially a refuge on wheels that can be driven out of the tunnel. So I've tried to skip through those fairly quickly. Apologies if it's a bit too quick, but I thought we'd go some key numbers because engineers always like numbers. And I think some of the numbers are quite remarkable. So the greatest distance we have between any egress point in the tunnel is 15,800 metres. The current tunnel length, as we've stated, 29.3 kilometres. So for context, for those of you that live south of the Thames, that would be from this room to Red Hill. And for anyone north of the Thames, it would be from this room to the edges of St Albans. So it's quite some distance. The conveyor belt, it's a single belt. We've got 3 boosters in line. And the conveyor belt currently is about 59 kilometres. The finished tunnel length, nearly 37 kilometres. And for one revolution of the conveyor belt at the minute, it's 5.5 hours. And to date, on site, we've manufactured 131,000 segments, which is 89% of the total. So we're not quite finished yet. It feels like we're nearly there. There's another 7 kilometres to go, which is a decent job in its own right. But I think it's testament to the teams that are involved. And I know we talk about collaboration a lot on projects, but I think this is truly an example of it. We've got the merging of mining technology, mining regulations with a tunnelling approach. And I think it's been really refreshing. Anglo American have been a dream to work with. We've got a really unified team and everyone's got the same purpose. So I think that's been reflected in both the performance, but also the fact that the retention of people on the project has been so consistent throughout. So I think on that note, I'd say thank you to all the teams involved. We've put a number of suppliers on here who have been involved in the project. It's very difficult to get everyone, but without the teams, Anglo and the Mines Inspectorate and all of those suppliers going, we probably wouldn't be as successful as we are. So I think it's been a fantastic team effort. I think I'll leave it there.
Okay, thank you to all our speakers. I'll take the first question, please. Have we got any microphones? Yeah, just coming down. Just down here.
Simon Wheeler. Question I had is, what happens with all the sediment at the end?
Of the shaft.
For the shaft sinking?
From the shaft, from the tunnel, what is the end use for it?
Yeah, so I'll answer from the shaft perspective, and then...
But you can do the spoilers as well.
I'll do the spoiler as well, yeah, why not? So from the shaft perspective, as I shown, there was a large lagoon that we used for sedimentation. It's built in a way that there's weir walls and break-offs so that we can intercept the majority of the cuttings and take those away. But there were some lessons that we learned on how we set that up and how we managed it, because ultimately at the end of the programme there was a process to go through in terms of drying up those spoils and removing them from site as a waste. And then from the tunnel side of things, so all of our material is taken back to Wootton. We've removed around over 2 million tonnes of material from the Wootton site. A lot of that has had some beneficial reuse. So over the road from us at Wootton, there's a Redcar bulk terminal. There's a lot of potentially contaminated land. So the material is taken out of there, it's compacted to create a level playing field to then construct and build on. With a lot of investment in Teesside, it's been a winner on that side of things.
Okay, Steve.
Steve Parker, Keystone Tunnelling. Thanks, guys, for a great presentation. The grout, 18 kilometres you said were pumping. How did, well, what diameter pipes did you use? And what was the mix? And was it retarded, accelerated on the TBM? And what sort of set times did you get, hour or 12 hours? Or was it just water?
I might redirect that to the guys from MAPE, who I think are in the... No, it was... it was retarded, so it's a two-component mix. The part B, the accelerator, the sodium silicate was taken down in IBCs. Grout is batched on surface, the cementitious part. It's pumped down a steel pipeline, 2-inch, and pumped down from Wootton through to the TBM. And then we moved the grout plant from Wootton to Lockwood Beck, and that meant it was going down a 380 metre shaft. That gave us some problems. I can probably talk for several hours about the grout that we've had, but trying to make sure that the grout stays moving but stays continuous through that pipeline. We did see problems towards the end where the quality dropped, and it was the retardation of it wasn't guaranteed at being 24 hours. The pumpability dropped from Lockwood Beck, whether it was partly to do with that massive head in the shaft, most likely, and we did have to resort to using IBCs on the trains for the last literally few hundred metres to get us past Ladycross.
Did you regularly flush the grout?
So yeah, we regularly put balls through the line. So we regularly put balls in. When we were in full production, we would also pig the line. So harder pigs that would go through and take out sediment. Sediment was a problem. We did have to flush with water as well, and regularly, or at several stages, we were removing pipes that had sedimentation, but it was always worthwhile keeping that pipeline as opposed to going to any form of grout cars or anything else.
Excellent, thank you.
Okay, one here.
Hi, Glenn Williams. On the Ladycross shaft, you mentioned that you actually grouted to prevent water ingress into the shaft. What were the considerations given to grouting? Perhaps an alternative method could have been ground freezing. So if you could give us some insight to why you chose grouting.
So the grouting for the actual shaft construction is very much related to the method itself. So with the blind boring methodology, part of the sequence is to grout the casing into position. And yeah, as Ashley kind of touched on before, fundamentally we're trying to cut off any water connection from surface down into the tunnel. So we
But you were drilling grout holes prior to the sinking of the shaft, is that correct?
Correct, sorry, apologies, yeah. Again, it's part of the process. An option could have been freezing. We'd have to obviously look at the cost, the time, also the potential impact of freezing the ground that you need to flow within the shaft. It would be, I think, possible, but it would be quite complex, whereas the pre-grouting is a tried and tested solution.
Thank you.
I think in addition to that, that location at Ladycross is within the North Yorkshire Moors National Park. It's a pretty isolated spot, and there was no sufficient power supply that could be used to facilitate ground freezing. So it would have required a huge amount of generators to do so, and it was deemed not practicable in a sense.
Okay, I worked on the Selby coalfield back in the late 70s. We used ground freezing for all the shafts there.
Okay, I've got a question online. This is from Stefan Gonichon. Very interesting presentation. Did you test and or use microfine or ultrafine cements in pre-grouting for the shafts?
So there was a difference in approach between Lockwood and Ladycross. At Lockwood, we didn't need to use microfine, but at Ladycross there were additional constraints because it was in the national park and we were quite close to spring lines on the side of the hill. So we were just at the top of the hill on the shaft site, but not too far from us, downstream, going towards the River Esk. We had to be mindful of not polluting those water supplies. And that's why we selected the microsilica approach. And it was probably quite unusual, I think, in the quantities of microsilica that we used, and taking it for that approach for pre-excavation grouting, because we weren't grouting small sort of sands, small pores. It was using fairly large volumes, but getting the balance right on the two components enabled us to grout up the fissures and prevent the water flow through the drilling location. But it was largely environmental constraint there that precluded us from using cementitious material.
Thanks. Okay, any more questions? Yeah, one down here.
Mike McLaughlin from Rockmate. Regarding the methane, was there any coal measures? Did you at all? I couldn't see any in the sections.
No, thankfully not. There were no coal measures. So the methane source is from within the mudstone. So there is organic material within the mudstone. It typically isn't a problem, but it can gradually desorb. So it's typically held in sort of almost microscopic levels. But as you break the rock, it's released into the air. So the majority of the time we see a very low background level of the monitoring into the cutterhead. But it's entirely manageable through ventilation and well below any set points. It's just that one instance in November 20 where we had the larger inrush, and I think it's probably still debatable as to how that volume of gas was held in the rock. There was no discernible significant fault in that location, but there must have been a discontinuity that was holding the gas in that region. So no coal measures. There are ironstone workings which are above the tunnel alignment, and there was concern earlier on that those ironstone mines could contain water with dissolved methane in that could have a pathway to the tunnel, but that was proven not to be the case.
Thank you.
Okay, question here.
Hi, I'm Asal from LBA. Brilliant presentation. Just one question. There was a lot of talk about some technology transfer between mining and tunneling in general. So can you give me a significant technology transfer, in your opinion, that happened between mining and tunneling and vice versa for this project?
Not so much about technology, but a lot of the things that have transferred from my perspective have made more to do with the requirements of the regulations, you know, things around self-rescuers, and one thing that Tom mentioned was the lighting stations in the tunnel, where conventionally hop-ups I think are mainly used, and this is one of the things that came after an intervention with the mines inspectorate, mass transport intervention. They wanted to see a safe refuge, so STRABAG went away and designed what we call the lighting station, so it's actually a safe space in the tunnel where, rather than standing on a hop-up with a train going next to you, people are actually getting behind a barrier and they're away from the actual moving transport. It's just things like that that have been, I think, a benefit on the project that's come over from the mining side.
Yeah. I think the refuges and the self-rescuers are probably also worth noting. The investment in having safe refuges underground, so our capacity underground is 48 people. That's driven by the safe refuges that we've got. There's a capacity of 28 for the TBM. The rescue train, so an independent refuge that is essentially a steel box that can support 20 people for 24 hours on wheels. There's always one parked underground at the rear of the TBM, and the second one is always parked on surface for a rescue event if need be. The requirement to have self-rescuers on your person or within reach or within arm's reach has driven a lot as well, given the length of the tunnel. If you're 29 kilometres into a tunnel and you've got an issue with the train that's blocking, so you can't egress via a train, and you have to walk out, a 60-minute self-rescue set's not necessarily going to cut it. So we've had to install changeover pods, so these pods on the sidewall of the tunnel, every 1,000 rings, 1.5 kilometres, where you can go in the event of emergency, take off your existing self-rescuer and change for a new set. So 48 people underground, but we have to have over 1,000 self-rescuers on site to make sure that capacity for that emergency scenario is covered.
Thank you.
All right, got another one from online, and then we'll go at the back. This is from Anthony Francis. Great presentation and a great engineering feat. Have Anglo established a marketing and sales strategy for the polyhalite?
It's a work in progress, but yeah, there's a lot of work gone into the marketing strategy. That's about all I'll say on that one.
Okay, thank you. All right, yeah. Shaney.
Thanks very much. A really very interesting presentation. I noticed that the segmental lining is steel cage reinforced. Were steel fibres considered for that, for the reinforcement? And might it have been mining regulations that prevented their use?
No.
No, I think it's the overburden that drove the requirement for the reinforcement cages, and as far as I know, there's no reason from the mining regulation side why it couldn't have been steel fibres.
All right, more questions, anyone? Yeah, Donald at the back there.
Donald Lamont. I was head of tunnelling in HSE up till 2010. I'm also chairman of the British Standard on Health and Safety in Tunnelling. And I would take issue to some extent with some of your comments on the benefits of working under mines regulations. Refuge chambers have been used in tunnelling for quite a long time now. Self-rescuers, which did start off in the mining industry as filter self-rescuers, we use oxygen self-rescuers when they're still using filter self-rescuers in the mining industry. And the lack of a walkway is probably not in accordance with BS 6164, the standard of health and safety in tunnelling. The lighting stations are not probably the sort of thing we would have had. We'd have had a walkway with a guardrail separating the train from the people. So I would challenge some of the benefits of working under the mines regs. I would also say that I've done work in New Zealand where the mines regs apply to all tunnels, and I'm not convinced that mining regulations are necessarily the best for tunnelling.
Yeah, I mean, that's a fair point. The mines regulations, we found out they don't exactly fit a tunnel. Things like, you've got regulations 48, which is 2 exits from a mine. So a tunnel, by its very nature, doesn't have 2 exits until you're connected to the shaft. So that was one of the problems that we had to overcome. You wouldn't normally have an 18-kilometre single entry in a mine. So it's just trying, it's not been easy to adapt the mines regulations to the tunnel. I take your point about BS 6164, which isn't legislation, of course. It's
only guidance.
Yeah, it is, but I've read it, and it does align a lot with a lot of the stuff in the mines regulations about safe refuges and about self-rescuers. It's definitely more appropriate than CDM on its own, and it's a good document.
Okay. Any more questions? Where are we? Okay.
Hi, David Kellett from Hunter Person. Thank you. Great presentation. Great project. I just wondered if the single TBM was on a manufacturer's buyback. Just as a joke. But no, the actual question is on the labour supply. I think for the TBM it was largely self-delivery. I just wondered if there was challenges, you know, and some further information on the management of the labour force. Thank you.
So our labour force, both in the segment factory and the tunnels, has been directly employed by STRABAG. There's been a big push in the local community to give that benefit to the community. So I think around 70% of the staff, including the workforce, live within 50 kilometres of the site. So there was a real big push, direct employment for all the staff, and then we can manage the training. We managed the welfare of those people, and we've had very good continuity, very low turnover, and also we think it's beneficial to the health and safety performance as well. So we've got long-term control over the training and real commitment from the team.
All right, maybe one more question, if anyone's got one. All right. Okay, I'd like to thank our speakers for an excellent presentation on a project we haven't heard that much about, really, so lovely to hear it tonight. Thank you. Just a couple of announcements, and then we'll close for the evening. Right. Yeah, can you move it on, please? There you go. I'd just like to say as well, it's great to see so many people out tonight. The last two meetings we've had really good attendance, so it really helps everything, really. And if you haven't signed the little sheet, can you make sure you do, please? Have we got copies of those sheets anywhere? Where are they? Yeah, they're at the back there. So just catch up with them after. It is important that we record the numbers with some dealings we've got with the ICE. So yeah, Food and Drink is sponsored by STRABAG. Next one, please. Just a quick show of hands. How many have bought the book? All right, not everyone. So everyone these books have gone around the world. Only last week we got one into Mexico, New Zealand, Australia, and the feedback we've had is marvellous. They are still available, but there's only a limited number. Just go on the BTS website, 900 pages, brilliantly referenced. Anyone you know who works in tunnelling or anything, it's all at the back. You can find a story about them. So, yeah. Next one, please. So Harding Prize, this is our next evening meeting, where younger members of the industry will do a presentation on a project they've worked on, and one of them will win the prize. So that's the 20th of March here. Yeah, next one. Okay. The annual dinner, it's not our normal first Friday in May. We couldn't get that this year, but and everyone knows, I'm sure, it's 23rd of May, and that's for this year only. Next year we'll go back to the first Friday in May. So, and I think ticket tables wise, my sheet tells me how many tables that is. Oh, there it is, yeah. You can see it's over half full already, so get in there quick. Next one, please. All right, so booking is now open for the very popular BTS Design and Construction course at Warwick University. 5-day course, and again, that's always fully booked, and we get great feedback. That's been running for many years, and many of the industry leading lights give presentations there. All right, next one, please. So on Thursday, the 20th of February, these young members have got a lot going on here. So on the 20th, there's a webinar at 12 o'clock, and then there's a social Acton Depot Museum meeting. Looks like a visit, sorry. And then on Thursday, the 6th of March, there is a lecture, but there's also an International Women's Day. Done a lot to promote this, which is really good, which will be after the lecture, the evening lecture. Thursday, 6th of March. Next one. Another young members. Thursday, the 20th of March. There's a workshop on SRFC and low carbon segment linings. All right, next one. Announcements then, another one for the young members. The Doug Allenby Memorial Medal. This was presented for the first time last year. It's for younger members of the tunnelling industry who have gone above and beyond. So these awards are really good, and they're inspiring to people in the industry. And there's also a bursary available there for the World Tunnelling Congress, a visit in 2026, which the BTS sponsor, again, to broaden the field of experience of the young members. Another one for young members, 24th of October is a one-day conference, so a bit of a way away yet. And the final one, I think. Yep, if you want to scan that, you can. All those people who didn't put their hands up, I'm expecting the phones up. So, okay, thank you everyone. See you in the bar.
Very good.